NASA just dropped a major alert about Triatlas that fundamentally changes everything we thought we knew about this visitor. By all logic, this comet should be dying right now. We are weeks past its perihelion. It's moving away from the sun, and it's cooling down. And following every prediction model we have, its activity should be dropping off smoothly. Instead, it's doing the complete opposite. The brightness isn't fading the way it should be. New shells are appearing in the coma, and there are fresh bursts of activity that simply weren't there before. The tail is actually sharpening rather than dissolving, and here is what makes this impossible to ignore. The non-gravitational acceleration hasn't dropped. Those gas jets are still firing and pushing the comet around weeks after they should have shut off. NASA's newest orbital calculations confirm that Atlas is still steering itself with gas vents when it should be behaving like a dead rock driven purely by gravity. You should stay tuned because what we're seeing is an object defying every model we have, exhibiting behavior never before seen in an interstellar visitor. Nobody knows if this is the final act and the build-up to something catastrophic. And let's break down exactly what NASA just confirmed. We have to start with baseline expectations because understanding what's supposed to happen makes what's actually happening so much stranger. When a typical comet swings past the sun, there's a predictable pattern. It approaches from the outer solar system, solar heating vaporizes surface ices, and gas carries dust to create the coma and tail. You see peak activity at perihelion, followed by a smooth decline as the comet moves away and cools after perihelion. Activity should drop off in a nice curve because less heat means less gas, the coma shrinks, the tail fades, and the whole show gradually winds down until you're left with a dark, quiet rock drifting back into deep space. That's the script and what our models predict for the vast majority of comets. However, 3I Atlas is not following that script, not even close. This object passed perihelion weeks ago, and based on its distance from the sun, it should be noticeably dimmer by now. Brightness should be dropping at a steady rate, and gas production should be falling as everything winds down. But when astronomers compared brightness measurements from last week to today, something jumped out immediately. The comet hasn't dimmed the way it should. While it is slightly fainter than its peak, the drop is way too small for how far from the sun it is now. If you overlay the predicted light curve on top of actual observations, they match up at first, but then right after perihelion, the real measurements peel away from the prediction. The predicted curve drops smoothly, while the real brightness runs flat, as almost like the comet looked at our predictions and decided to do its own thing. What this means is that 3I Atlas is still pumping out gas and dust at a rate more consistent with being close to the sun than being on the way out. It's acting like it's still being cooked, even though it's not. You might think maybe there's some leftover glow or residual material hanging around in the coma that's taking time to dissipate, which could explain sustained brightness. Except the latest images completely contradict that explanation. When astronomers took the newest deep exposures and stacked them to bring out faint details, what they saw was not a coma fading quietly. Instead, they saw structure, layers, and active feeding, and the coma is being actively fed by fresh material. You can actually see multiple shells in the inner coma, which are faint arcs of gas and dust nested inside each other like tree rings. Each shell represents a pulse of activity or a burst of gas escaping from the nucleus. The outer shells match earlier pulses we already knew about, but there's an inner shell that is brand new. It wasn't there in earlier image stacks, it just showed up. That means at least one new burst of activity happened recently, not weeks ago near perihelion. But late in the game, when things should be calming down, when the comet should be getting quieter, it instead had another outburst and threw off another wave of gas and dust. And the tail, instead of shrinking into a thin streamer, is still crisp and defined. The latest images show a sharper, more defined spine, which is a bright central line of dust running down the middle. That's exactly what you'd expect from an active jet or a vent on the nucleus that's still firing and hasn't switched off yet. Here is the most telling part buried in NASA's alert: the orbit solution. Every time new position measurements come in, NASA updates the orbital calculations to track where the comet's been and where it's going. To get those calculations accurate, they have to account for non-gravitational forces. While most space rocks are driven purely by gravity, comets are different when they are actively venting gas. Those jets act like tiny rocket thrusters. Gas shooting out in one direction pushes the nucleus in the opposite direction. Following Newton's third law, those little pushes add up and change the comet's trajectory in measurable ways. So orbital calculations include non-gravitational terms, extra accelerations accounting for jets pushing the comet around. If 3I Atlas were coming down and its jets were switching off, those terms should be shrinking. The comet should behave more like a dead rock driven almost entirely by gravity. And that's not what the new calculations show. The magnitude of non-gravitational acceleration hasn't T-collapsed. It's holding steady, and in some directions, it's even a hair stronger than it was a few updates ago. This means the jets are still firing, the comet is still pushing itself around, and it's still steering itself with gas vents weeks after perihelion when it should be shutting down. So to understand what's going on, think about how heat moves through a comet nucleus. It's not like heating a rock in your oven where everything warms evenly. Comets are porous, layered, and full of pockets and voids. They are mixtures of ice, frozen gases, dust, and rock, all jumbled together. When the comet was near the sun, the surface got cooked first. Solar radiation heated the outer layers, and the ices there vaporized, giving us wild early activity and dramatic outbursts near perihelions. But heat doesn't stop at the surface. It conducts inward and migrates down into deeper. This isn't a fast process. It takes time. So right now, even though the comet is farther from the sun and the surface is cooling, there's still a heat wave moving through the interior. It's reaching pockets of ice deeper down that haven't been touched yet. Some of these ice pockets have been frozen for billions of years, possibly since this comet formed in another star system, maybe even before our solar system existed. And now, for the first time in billions of years, they're getting warm. When those deep pockets finally cross their threshold temperature and get hot enough to vaporize, they don't care that the comet is technically farther from the sun or that it's supposed to be calming down. They vent anyway. The ice turns to gas, pushes through cracks and fractures in the overlying layers, and bursts out at the surface. That's why the activity curve has bumps instead of a smooth decline. Each bump is a new layer waking up, a pocket reaching its vaporization point every time that happens. It's gas from a different location inside the nucleus, from a pocket under different pressure with a different chemical composition, finding different routes to the surface. New fractures open, old fractures widen, and the balance between vents shifts. From the outside, we see new shells in the coma, new structure in the tail, brightness patterns that don't match predictions, and non-gravitational acceleration that refuses to go away. Here is why this alert matters. An active comet is under constant stress. Gas pushing through cracks exerts force on surrounding material. Jets firing from off-center points create torque, twisting the nucleus. If the rotation changes from jet activity, that changing spin pulls on weak regions and creates stress patterns. And we've watched comets in our solar system follow this exact path. They stay active when we think they should calm down, and then one day they aren't a single nucleus anymore. They become a string of fragments. The stress was simply too much. A fracture propagated through, and the comet broke apart. Right now, there is no confirmed split in 3I Atlas, The core still looks like one object, but if this comet stays active this long at this intensity, the risk grows every single day. Every new layer that vents adds more torque and more internal pressure trying to crack the nucleus open, and there is more thermal stress as different parts heat and cool at different rates. If activity tapers off in the next few updates and everything winds down, this is just one more wild chapter in an incredible story. But if activity keeps hanging on, if more shells keep appearing, and if the non-gravitational push refuses to drop, we are in uncharted territory. We're watching an object from another star system stay alive longer than models predicted and push itself harder than we thought possible. Nobody knows what that means. Is 3I Atlas heading for a breakup? Or does it have internal strength we haven't accounted for? Drop your prediction below and subscribe for updates as NASA tracks this daily. We are literally writing the textbook on interstellar comet behavior in real time,